So we're going to talk about estimation. So let me first talk about the data structures that we typically use. And they really come in one of two main sources and a combination of them. So the first is market level data. And what we mean by that is either a cross-section or a time series or panel of different markets, right? So for now, think of it as different geographical markets or a national market over time. Okay, and we'll talk a little bit more about what I mean by that in the next slide. The other type of data is consumer level data, where typically what we'll just have is a cross-section or a sample of consumers. Ideally, if we can, having a panel is going to be extremely useful. So a panel, with the idea that we actually get to see people making repeated choices in different economic environments, that's really going to give us a lot of identifying power. And sometimes, but this is rare, although I think Ariel is going to talk about an example of this tomorrow, we will have what's called second choice data. So we'll see what product people actually chose, and then we might have a survey of them saying, had I not chosen this car, what other car would I have chosen? Right? So in some sense, we get to see not just their first choice, but also their second choice. And that's, again, you can see will have a lot of identifying power. Sometimes we'll have combinations, and again, that's going to be very useful. And the combinations could be, we could either have a sample of consumers, so know exactly what those consumers chose, but then have some aggregate market shares. Or we could have, things like we could know the quantity share by demographic group. So we could know let's say the share of people that buy a Mercedes by their income group. So that's going to be very useful. Or we could have the opposite of having the average demographics of people that, let's say, buy a Ford. Right? So all that information is going to be some sort of combination. That's going to be very useful. For today's lecture, I'm just going to focus on the first. So we're assuming we only have market level data. And in the following lectures, either later this afternoon or tomorrow, we'll talk about how to bring in this additional information that we have here in these other data sets. So let me just go a little bit in more detail what I mean by the market level data. So what we get to see is at the product level, we get to see either the quantity or we're going to convert that to market share by market. And I put market here in quotations because sometimes it's not quite obvious what do we mean by market. Right? And we'll see kind of what the model means. It's really, it's going to be well defined within the model. Sometimes you have to figure out how to translate that into the data. So the data is going to include some aggregate quantity at this market level. It's going to have price and characteristics, advertising, or other things that we think are important, again, for each of the product at this market level. What we're going to need is we're going to need a definition of the market size. And this goes actually to a question that Dennis asked at the end of last lecture. We're going to need this definition of the market size so we can actually go from quantity to market shares. Now, what's tough here is that this is going to include purchases of the outside good. Right? So it's not, unlike the inside good, you could say, well, we just sum over the quantity and divide by that. What we need here is we need to know how many people did not decide not to buy cars. Right? So how do we know that? Right? So if we have a sample, we could see, okay, let's take 100 households and see how many of them bought a new car this year, and those that didn't chose the outside good. But if we look at the aggregate, we need to somehow define what the market share was and or what the market size was, and we'll see ways of doing that. The other thing that's going to be very useful, although it's optional, is to have some idea of the distribution of the consumer demographics. Okay, so we're not going to have, this is going to be aggregate data, so I don't have individual specific demographics. All I need to know is the distribution. Right? So if I think of, this room is a market, and the next room, the productivity guys, that's a separate market, and then the IT guys is another market, I'd like to know what's the distribution of the demographics within each of these markets, even if I don't know individuals. And we could get that either by having a sample of actual consumers, things like the consumer, the CPS, or the consumer expenditure survey, so we could literally have consumers then do some kind of non-parametric distribution for this demographics, or we could actually use some sort of data to try to estimate a parametric distribution. So for example, if it's income, we might say, okay, we have some general income, we're going to fit some kind of log normal curve to it and just use that data to fit that. And again, we'll see how to do that. So the advantages of market level data, this is compared to consumer level data I'll talk about on the next slide, is that it's much easier to get, right? Because you might ask, well, why do we even bother with this market level data? Why don't we just go and do everything with consumer level data? Well, in many cases, you don't have it, right? So it's sometimes getting the market level data, especially quantities, can be difficult, right? Prices, you could just, sometimes you want to know what are the prices of a product right now, just go look on the shelves, right? Quantities is a little bit harder, but still much easier to get than actual sample of consumers. And this is true not just for us as academics, but also a lot of times, for companies. For example, Nielsen, that collects a lot of data, they have a consumer level panel, and over the years they keep thinking of shutting it down just because it's too expensive to actually collect it. Right? They still have it in place, but they keep thinking about it. The other advantage that this has is it does really give you, in some sense, the whole population in the market you want. And when we talk about consumer level data, I'll talk about sample selection issues, and it's going to be less of an issue here. The disadvantage, of course, is that the estimation, as we'll see, is going to be harder, and identification is going to be a lot murkier. So that's obviously a disadvantage. So consumer level data, the main thing that it gives us is we actually have a match between consumers and what they purchase. Right? So if I have aggregate data, I have, this would be a market, and I know, what share, how many of you drink water and how many of you drink iced tea. Okay, that would be the market shares of my two products. If I had consumer level data, I would know each one of you specifically what you chose. So obviously I have the consumer choices, including here I'd have the outside goods. I see how many of you decided not to drink anything. Right? So that would be the outside good. A key challenge, by the way, in these data is getting, even if you have it, is getting the price and characteristics of all the options. This is especially problematic when different consumers pay different prices. Right? So think of, for example, I have a sample of consumers and know what autos they bought. Okay? Now, I know what price they paid for the option they chose. I might know the MSRP for the options they didn't choose. But we know that most people do not pay the MSRP. Right? So now I have to figure out what would they have paid if they'd gone to another option. Right? Now, you could say the same problem also exists in the aggregate data, but here sometimes actually collecting both the prices and the characteristics of the available options is actually quite problematic and quite difficult to do. And the other thing that I'd like to have here is actual consumer demographics. If I don't have actual demographics, there is a sense in which the individual data is really just the same as market level data, that there isn't really any much more information or useful information there. So what are the advantages of this? Obviously, if I want to see the impact of demographics, this is a much kind of more straightforward way of doing this. Identification and estimation is easier. And when we start talking about dynamics, which we'll do at the end of the day tomorrow, consumer level data is going to be much more useful, right? Especially if I get to see consumers making repeated choices. There is a sense in which at that point your identification off of aggregate data, although we'll actually see a paper that does that, is very questionable. The disadvantages, of course, harder, more costly to get, but there's also issues of both sample selection, right? So if it involves, who's willing to actually participate, right? As opposed to kind of having aggregate data that's more administrative, right? Could actually come from stores or from firms. Here, if we actually have to follow consumers, who is willing to actually participate in the sample, and to the extent that we need to have people record what they do, there might be some reporting errors and things that we might worry about. Okay, so with that in mind, let me just kind of quickly review the model and the notation, because most of this was in Ariel's slides, but maybe slightly smaller font. So let me just kind of go through it quickly and make sure we're on the same page in terms of notation. So we're going to work in characteristic space, and the starting point is going to be this indirect utility from the J inside goods, right? So the utility is going to be a function of xjt. These are the observed characteristics. This xijt, which we'll get back to, this plays an important role here. That's the unobserved, to us, product characteristics. Everyone in the market is going to assume to observe that. There's going to be two types of demographics, and here my notation is slightly different than Ariel's. There's going to be observed consumer demographic. Now I put observed in quotation mark because we're working with aggregate data. So we never actually observe, but these are the type of things that you could get a sample for, right? So think of this like income. So I might be able to estimate the distribution of income in a market, but it's not that I observe it for any particular individual, right? So that's what I mean by these DITs. The VITs, or the news, what Ariel called them, these are the unobserved consumer demographics. Okay, so these are things that you think, even if I had individual level data, it's unlikely that I would actually observe. Okay, so example I like to give is if you think of a purchase of cars, right? So let's say the number of dogs you have might matter for whether, the size of the car you'd like, right? And in most consumer panels, we don't actually see that, okay? But although now more and more you can see it. Okay, but that's going to be the notation. Now, xijt, this unobserved characteristic, is going to play an important role. And first, you could think it's realistic because it's going to capture the idea that there's some characteristics of the product that we do not observe, right? So it doesn't matter how many X's we put in there, there's still something unique about the product that we really can't capture, right? So that's going to be one. It will act as a residual or as an econometric residual, or when we go, econometric error term when we go to the estimation. And it's also important because without it, especially when we're working with aggregate data, we're faced with this problem often called the overfitting problem, and that's the problem that we don't know why we're not perfectly fitting the market shares, right? We need some sort of an error term to tell us this is why our model doesn't perfectly fit the data, and that's what this psi is going to be. It's going to act as a buffer. However, it will potentially imply endogeneity of some of the characteristics. The one we usually care about is price. Okay, now a common model that we're going to use, well, a model that's used a lot, and the one that I'm going to use for this lecture, and actually for most of our lectures, is something that's often called a random coefficients Logit model or mixed Logit model. Okay, so that's a particular specification. So what we have is the utility for individual I from brand J at market T is xjt times beta I. So different individuals value these characteristics differently, plus alpha I times pjt. So again, alpha I is the marginal utility of income times the price, plus this psi jt plus epsilon I jt. That's going to be the Logit error term. Okay. Now we're going to assume that these taste parameters, alpha I and beta I, are distributed. They have a mean, alpha and beta, that's common to everyone, and heterogeneity around that mean. So the random coefficients, or the mixed Logit part, basically says if we don't have these two components, right? So if pi and sigma are 0, then we basically collapse to a Logit model, right? If we make the appropriate assumptions on the epsilon. Okay, so that's the way in which we're going to kind of generalize the Logit model. Going back to the issue of the definition of the market, you can see here in the model, the market is defined in some sense clearly, and it basically says the market is the level at which these things don't vary, right? So if you look at the x, the p's, and the xi's, right, they're all indexed by t, so they vary across markets, but not within a market. So within the context of the model, that's kind of how the market is well defined, right? We could basically say, all right, let's take an area and a time period in which these things are constant. Now, of course, when we go to the data, we're going to have to make some assumptions about this, right? Because when we go, for example, if we're going to define the market as annual, let's say nationally annual market, in the case when we're looking at automobiles, we know that prices are going to vary both across geographical regions and across individuals, but here they're assumed to actually be constant. Okay? There are extensions. You could ask, well, what happens if these prices vary? There are extensions of that, but for the purpose of what I'm talking about now, we're going to ignore that. Now, it's going to be very convenient for what follows to separate this utility into three different parts. The first part is the mean utility, right? So it's kind of defined here. It's basically saying, let's just take everything that doesn't vary with I, right? So it's xjt times beta plus alpha times pjt plus the psi jt. Okay? So that's the mean utility. It's the mean across individuals. The second component is this mu I jt. So it's basically the interaction of this heterogeneity in the parameters with the price and x's. And then finally is the epsilon term. Okay? Now going back, Dennis, to kind of the question that you asked Ariel about, are there other ways of generating correlation? So remember, the problem that we have with a simple Logit model, right? So what does a simple Logit model do? It sets this part to 0, right? Because this is going to be 0, and assumes this is IID. Okay? Also extreme value, but the key thing is that it's IID. So what that means is if you actually get a shock, let's say price of a particular product increases a little bit, well, that's no longer, for people on the margin, that's no longer going to be their first choice. So then the question is, where are they going to go? Okay, what's their second choice? In the Logit model, there's no correlation, right? Because this is common to everyone, this is 0, and this is IID. So I'm basically saying my second choice is going to be like the average of the market. Right? And that's why substitution patterns are proportional to market shares. So what we want to do is we want to create a correlation structure between the utility. Right? So if you have a high utility from Mercedes, you're probably also going to have a relatively high utility from a BMW, right? Relative to the average consumer. Right? So there's two ways of creating this correlation, and it could come through either of these components. Okay? So let me actually, I've already kind of gone through this is kind of the second point here, and we can actually create this correlation in kind of through either of these, right? So we can continue to assume that this is IID, right, and create the correlation through this term here. And what this means is now that products that have similar X's, similar characteristics, will be correlated, and consumers that have similar demographics are going to have similar taste, right? That's how we can create the correlation. Or we could say, you know what, forget this, forget the random coefficients part. Why don't we start putting distributions on here that are not IID, right? And that's what things like the nested logit does, or kind of, for those of you who are familiar, there's a more general class called the GEV, the general extreme value, and that's what it tries to do, is say, let's put the correlation structure there. Now, just doing an unrestricted correlation structure, we're back to the too many parameters problem, right? Because remember, there's J of these, right? So the correlation structure, right, it's basically J squared, or J times J minus 1 divided by 2, right? All the correlation. So there are ways that we could create this correlation, right? But we're either going to do it through this part or through here. Now, there's potentially hybrids. There are some papers that we're not going to be talking about that will go back to the GEV framework and say, okay, we want to create this correlation, but maybe we're going to create it through some characteristic structure on this correlation structure rather than through here. I don't have time to fully talk about them, but there are ways in which to incorporate it. Okay, so that's kind of the interplay. Let me just sort of stress this delta. I'll refer to it a lot. It's going to play a key role. And the key role is the fact that this delta, basically, let me go back to the definition, just one slide up. The delta, you see, the psi, this residual, is going to appear only in it, right? So it doesn't appear in the other parts of the model, and that's going to be very important for the purpose of estimation. Okay? The other thing here is, if you see here, I actually split, before I had all the parameters just theta, and I split into theta 1 and theta 2. And the reason I do that, theta 1 are the parameters that enter into this linear part. Okay, you'll see later why I call it linear. It's going to basically enter our objective function in a linear way. And these are going to be the nonlinear parameters. Okay, so the theta 1 here, that's just going to be the mean alpha and the mean beta, right? Alpha and beta. And here, that's going to be these deviations from the mean, right? These, what I called pi and sigma, right? Those are going to be the heterogeneity parameters. Okay, and I'm going to refer to them as either linear or linear, nonlinear parameters interchangeably. Okay, and we talked about the definition of the market. That's basically the level at which these things vary. Okay, so the key challenge for the estimation, there's really sort of two key challenges here. One is the how to recover the nonlinear parameters, right? These are the theta 2s, the one that govern the distribution of heterogeneity without observing consumer level data. Right? So to the extent there's kind of any sort of rabbit coming out of the hat here, that's usually where people kind of struggle. They say, well, all you see is market level data. How can you actually get the distribution of heterogeneity within the market? And we'll see, we'll rely a lot, although we don't have to exclusive. You can actually even do this with a single market. But I think it's much more intuitive if you think of the fact that we see different markets, right? With different distribution of, let's say, demographics, and that's going to let us see the effect of these, right? So think of, I basically have market shares for, this market here, and then I have another market next door that has some different distribution of demographics, and I'm going to see how choices, the aggregate choices or the aggregate market shares vary, and that's how I'm going to try and identify that. The other key thing here is really this unobserved characteristic. So I know we kind of keep going back to it, but let me just sort of mention a few things. First is this unobserved characteristic is one of the main differences from the earlier discrete choice models. So by the earlier, I mean kind of the McFadden and others work kind of in the 70s and early 80s. These earlier models often had a option-specific constant, right, which is kind of like this XIGT with consumer level data, and we'll see it in a couple of slides. We'll see exactly how that fits in here. But whenever they went to aggregate data, they didn't have that, right? And having this in here creates a potential for correlation with price or the other axis. We're mainly going to be worried about correlation with price. So again, that's going to make another challenge, potentially another challenge for the estimation. The other thing, and this is not something I'm going to be talking about today, but will be an issue later on, is that whenever we're going to construct a counterfactual, we're going to have to decide what happens to the XIJT. And that kind of counterfactual could be whether we have a new good. We have to decide, well, what's the XIJT for this new good, right? You could say, okay, the X's I know, those are the ones I want to experiment, but what do I do with these counterfactuals. It's going to be very important when we do welfare. And even when we talk about dynamics, we'll kind of see how this fits in. So in some sense, it's going to be very realistic for estimation, but for a lot of what we want to use the model for, it's actually going to be problematic. So if we have consumer level data, you could say the first issue, the issue of how do we know the distribution of nonlinear parameters, I think, or at least intuition, is less of a problem. So, well, of course, you get to see different consumers and how they make choices, and that's how you're going to get some of these nonlinear parameters. The endogeneity problem, often people will say, well, I have consumer level data, therefore I don't have to worry about endogeneity. So let me just, this is a point I'll return to a few times. Just on the face of it, that argument is wrong. Okay, and that's a point that's often missed. If there's an unobserved characteristic, there's an unobserved characteristic. And if it's correlated with price, it's correlated with price. Right? And it doesn't, the level of data that you have just means that the way you can deal with it would be different. Right? But it doesn't mean that just because you have individual level data, it's not important. And after lunch, I'll actually show you some applications, and we'll see that. You can actually see that in real data. When people have ignored it, you can see it in the results. I mean, that's exactly what we would expect. Okay, let me just step back before talking about aggregate data. Let me talk and say, what would we do, just for intuition's sake, what would we do if we had micro-level data? Okay? The way I'm going to talk about it here is just for intuition. This is not the way that we propose to estimate the model. Ariel will talk about that in one of the future lectures. Here it's just for intuition, just to fix ideas, because I think once we understand what we can do with micro-level data, with consumer-level data, we can understand what we're doing with the aggregate data. Okay? So suppose we had micro-level data. One way to estimate this model with this xi in it is in two steps. Okay? In the first step, we're going to write what's the probability that individual I in market T chooses a particular brand as a function of everything, right? And in function of kind of all the characteristics. And basically, here we're going to exploit the fact that delta, right? Xi is where delta appears, right? So what we would do is we could say, you know, suppose I actually shut off the sigma part, right? So I have basically a logit, but with heterogeneity across demographics. This is what I would have, right? I would say it's this kind of exponential form, right? Where what I have here is I have the mean utility and the heterogeneity across the demographics. Okay? So the mean utility, you can think of it as just going to be a fixed effect, right? So it's going to be a market time fixed effect, and that's going to absorb both the kind of mean effect, but also this unobserved characteristic, right? So I can actually estimate this using maximum likelihood, right? And what I get is I get the estimates of the nonlinear parameters. Here, these are the effective demographics, and the mean market effect. Right? Now, to get the rest of the parameter, that's step one. The next step parameter, what I do is I take this thing that was estimated in the first step, and I'm going to project it onto the x's and p's. Now, if I think these x's and p's are exogenous in the sense that they're uncorrelated with this xi, right, then I can just do this using least squares. Okay? If I think there's correlation here, then I'm going to use instruments, right? But this is, you can think of it as a linear regression, right, where the dependent variable are the fixed effects from the first step estimation, and I'm just projecting them onto the x's and the p's that vary across products and across time. Okay? So there's many ways maybe why you wouldn't want to do this, but just in terms of, you know, this is a feasible and will yield consistent estimates. Okay? And the key thing here is to realize, you know, this psi jt is going to be the residual in this regression, right? So in some sense it's going to be the econometric residual here in the second step. Okay, so what's the intuition that we get from here? And I want to emphasize this because I'm going to try to carry the same intuition over when we go to estimate the aggregate or using aggregate data. So it's it's two steps. First, we'll recover these mean utilities, okay, which you can think of as just as fixed effects, right? And the theta 2, the parameters that govern the heterogeneity, and then we're going to recover the theta 1s, right? The kind of the mean effects. And it's important to realize that different variation is identifying these different parameters. The nonlinear parameters are identified from variation in demographics holding this delta constant, right? So we're controlling for basically the variation, if you want, across products and markets in this psi jt, right? It's an unobserved, by holding this delta with this fixed effect. And then we're just looking across different demographics how they're making different choices. Right? So that's what's giving us the distribution of heterogeneity. The theta 1 is actually now identified from cross-market or cross-product variation. Right? So I could actually also look across product, but you think probably more credible if you actually have it across markets, right, in this second, in the second step regression. So with market level data, we're in some sense going to try to follow a very similar logic. Okay, so we're going to try and follow these these kind of two steps of saying, let's first recover what the mean utility is, right, what was the fixed effect here, and then let's project that onto the x's and the p's, right? The only difference is we're not going to have the within market variation in the choice probabilities, right? Because all we get to observe is a single market share. I think of it as the average choice probability. We're not going to have that variation within a market. So we're going to have to, in some sense, for identification, we're going to have to rely also, even for this first part, for this first step, on cross-market variation. Okay, and really the key issue is the fact that psi jt, right, we don't get to see multiple observations where it's held constant. Right? That's kind of one of the main advantages of the individual level data, is that we get to see the choice probabilities of different demographic groups holding psi j constant. Right? Because with different markets, what we do is, at least for identification purposes, we can think of we have an infinite number of markets with an infinite combination of demographics, but what's changing is the distribution of demographics and the psi j's. Right? With individual level data, we get to see within a market holding psi j constant, what are the different choice probabilities. That's, essentially the difference between the two. Okay, so with that in mind, let me go kind of to the more specifics of exactly how we're going to estimate this with market level data. So one thing to step back and to say, well, we know that really how do we estimate things? We say, well, we have observed data. Here, these are the observed shares or observed quantities. Why don't we just choose the parameter that minimizes the distance between the observed shares and those predicted by the model, right? Why do you have to go kind of and do all this sort of complicated stuff you're about to do? Why don't we just kind of look at this nonlinear problem and just minimize that distance? So there's a couple of reasons not to do it. One, maybe not the most important, but kind of obvious, is the fact that there's a computational problem, because all the parameters are going to enter these share equations nonlinearly. And if we have a lot of parameters, that could actually be quite complicated. Okay? But we could sort of handle that. More importantly is the fact that if we want to allow for psi's, right, if we want to allow for what we kind of think of these as structural error terms, right, they're going to be buried inside here. So for one thing, it's not even clear how we compute this share equation, right, because, well, how do you compute the share if you don't know what psi is, right? But even if you know how to compute it, or you're going to do it, let's start with a guess and play. The thing is that psi is actually it's going to be correlated with price, and they're both buried in here, right? And so kind of standard linear IV methods are not going to work, right? So if there's a correlation between psi and p, they're both buried inside that nonlinear function, and we don't know how to do it, right? So if we want to have this structural error term, okay, so by structure here I mean the fact that we have an error term that we have in some sense a name for it. It's an unobserved characteristic, right? Then it should enter in here. If, on the other hand, we say, well, all we really want to say is, well, there's some reason we don't know that our model doesn't quite fit the data, we could just look at this difference. Okay, so for the estimation, what we're going to follow here is we're going to follow the basic idea that was proposed by Steve Berry in a 94 RAND paper and Berry, Levinson, and Pecos in the 95 Econometric paper. So this is the famous BLP that Nancy already alluded to in the introduction. And the key insight in this is the fact that, it's kind of the following steps, is the fact that when we have this psi jt, so once we introduce it, the market shares predicted by the model, right? So this is basically the same equation that Ariel had before, basically saying we're going to take for each individual what their optimal choice is, right? And then we're going to sum over those individuals that have J as their optimal choice, right? Where we're kind of integrating over the distribution of heterogeneity. So with that, you can actually get, right, you can play around with this residual so that the predicted market share is going to equal the observed market share, right? So we're going to play around with that. It ends up that under very weak conditions on the demand structure, you need some conditions, but weak conditions, you can actually invert this relationship. So you can write that this mean utility is this sigma inverse of shares, x's, and p's. Okay? And here, what's important is that psi only enters in the mean utility and enters in a linear way. Right? So the idea is after we invert this relationship here, right, that equates the predicted shares and observed shares, we can actually think of this just like in the individual level data that we took the fixed effect and regress them. So we're going to do kind of a very similar idea here. Is we're going to take these inverted shares and we're going to use them as a quote-unquote dependent variable in a linear regression. Okay? That's going to be kind of the key idea, right? Is that once you can do this inversion, the error term just appears in here. Okay, so before going to the details, let me just sort of emphasize one rule. And once we do this estimation, by the way, we're going to estimate the parameters via GMM, so it's going to be, we're going to use instruments for it. And the instruments here actually play two roles, and this is a point that's often missed. They are going to generate moment conditions to identify the nonlinear parameters, right? So unlike the individual level data, right, where we can estimate the nonlinear parameters from the maximum likelihood stage, here we need to generate some moments to estimate these as well. And then potentially they're going to deal with the correlation of the prices and the error. So the basic idea is even in situations, suppose you actually say, you know what, I don't think in my data price is endogenous, right? Because it was set by some experiment, right? I've actually heard people say that. Oh, so I don't have to worry about instruments. Well, it's true. You don't need to worry for instruments for the second stage, but you still need to generate some sort of moments in order to estimate these theta 2s. Right? And I've actually have seen students that, would occasionally come and say, well, I've estimated, I'm not worried about this, I've actually estimated without moments, and they actually get numbers because it's a nonlinear problem, but in some sense, really, they're not really identified. And in this last point, I think is often missed, that when we think about instruments, we're always thinking about instruments for price, but even if price is exogenous, we still need these additional moments, right, basically to solve, to have at least as many equations as we do parameters. Okay? And the reason this is really different from the consumer level data, because with consumer level data we don't have this problem, and that is because with aggregate data, all that we really know in the market is the mean choice probability, right? That's what the market share is, right? It's the average choice probability within the market. With consumer level data, we actually have more moments of those choice probabilities because we have they vary with the demographics. So we can use this additional information to actually estimate the theta 2s, which we don't have here. Okay? But otherwise, we're actually going to try to follow the same logic as in the individual level data. Okay? So what I'm going to go now is I'm actually going to go over the steps of the estimation. I'm going to assume that we have valid instruments. Okay? Yep. Yeah. Yes, but when we're estimating the model here, okay, with the individual level data, in some sense we've controlled for these things here, right? So there is no endogeneity here, right? Now, when we go to the aggregate data, I mean, maybe in a way what you're saying is exactly, a different way of saying what I've said there is the fact that we need moments to identify the heterogeneity parameters, right? So you're right in the case that if we actually go to a pure Logit model where there are no nonlinear parameters, then we're not going to need these additional moments, okay? But I think it's also the way we think about them, it's a little bit different, right? So when we think about price and instruments for price, it's, we should just follow our usual intuition from demand and supply models. When we're thinking about these nonlinear parameters, it's a little bit different, right? And whether you want to literally think about them as there's a correlation there, or we just need, if you want, a rank condition, right? That we want to have at least as many equations as we have parameters, then, you can think of it that way. Okay? Okay, where was I? Okay, so what I'm going to go is I'm going to go through the steps of the estimation. So for now, I'm going to assume that we have valid IVs. Okay, I'm just going to call them Zs, and they're there. After lunch, we'll talk about specific examples of how people have used them. Okay, but for now, let's just assume that we have instruments that satisfy the usual condition that we want, and we'll kind of see specifically what they are. I'm going to follow the original BLP algorithm. Those of you who have been following kind of the literature the last sort of few years, there's been some alternatives that have been proposed, okay, and I'll talk about them at the very end. Okay, some people might have preferred that I talk only about these alternatives, but I think just in terms of kind of building up and understanding this model, it's actually easier in this original algorithm. I'll talk about the alternatives later, and I'll also kind of, if we have time, I'll talk about the performance of the various algorithms later on. Okay, so the algorithm takes on to the following steps. The first step, I mean, there's a little bit of preliminary of data work, but I'm not going to get into that. So the first step is you need to compute the predicted shares by the model. So what you do is you're going to guess a value, or what you need is, you think of it, you're going to guess a value of the mean utility. You're going to guess a value of the nonlinear parameters, and then you need a function that's going to tell you that's the share that I get if those were the cases. Okay, that's going to be step number one, and we're going to do this step over and over again. Okay? That's going to be nested within what I call the inversion. So we're going to take the nonlinear parameters as given, and we're going to search for a mean utility that equates this share that was computed in 1 to the observed shares. Right? So for any given value of delta and theta 2, I can compute what the shares are, and I'm going to just search for that value that sets the observed shares and the predicted shares exactly equal. Okay, that's going to be this second step, and that's going to be kind of, this is what is often referred to as the nested fixed point algorithm, because basically there's going to be kind of a search here that's nested within a search for the parameter theta 2. Okay? But basically for any candidate value of the nonlinear parameters, I'm going to search for this value that equates the two things. Okay? Then once I found it, I'm going to use this computed value to compute psi jt. What do I mean compute psi jt? It's just that basically say this delta is equal to x beta plus psi. Right? So I can actually compute what that is, and then I'm going to fit this into a GMM objective. Okay? I'm going to go through all the details of this. It's just kind of the overview. And then I'm basically going to search for the value of the parameters that minimize the objective function, the GMM objective function. Okay? So that's going to be a search for the parameters, and it's going to nest in it within each candidate value. I'm going to do this inversion of the market shares. Okay? So let me go through these steps one by one. But before doing that, let me give you an example of how this works in the Logit model. Now, the Logit model, a lot of these things can actually be done analytically. So it translates into a very simple linear equation. Right? So to compute the market shares, well, we know that in the Logit model, these are the market shares. Remember, all the DIs and VIs, they're all set to 0 in the Logit, right? There's no heterogeneity. Okay? So these are the shares. Well, how do I do the inversion? Once again, here I can do this analytically. This is actually well known from kind of the fifth sheet, sometimes referred to as the Logit, the Logit inversion. And you basically take the log of the log of SJT minus the log of the share of the outside good, right? And it's just basically equal to the difference in these. This is, Ariel talked about last time, we're going to normalize this to 0, right? So what we have is that the mean utility, which is just equal to the log of this ratio of these two shares, is just equal to xjt beta plus alpha pjt plus psi, right? So this is a linear regression, right? A linear regression where the dependent variable is just the log of the ratio of the shares. Okay, and now if you think that price and X are exogenous, just do this using OLS. Estimate using OLS. So you normalize delta 0 to 0? Yes, so normally what we do here is we normalize this to 0. Right? This was kind of, Ariel talked about a little bit last time. We need to have some normalizations. Going back actually to a question that Dennis asked, one of the things we could do is if we have enough J's in here, we could actually put a market fixed effect in it to basically, right? So it would be a constant in here, right, that would basically pick this up, right? So you could you could do it, right? Or if you think of this as a time series, right, where t is a time series, you could actually put a, well, either a trend or literally a time dummy for each time period. And we can do that because we have multiple j's for each time period, right? So in principle, we could still estimate that, right? So that's one way to get, at least in the Logit model, around this normalization, right? But you see basically here, this amounts to a very simple linear equation. Okay? Now, with very few exceptions, one of them, another one would be the nested logit, which we'll see kind of later on. We're going to follow exactly this logic, except that each of these steps has to be done numerically. Okay? But that's basically the idea of what we want to do. Okay, so now let me go a little bit kind of through each of these steps. This is the place where I'm going to get, for some people a little bit too nitty-gritty, and for some people maybe not enough, but maybe on average I'll get it right, hopefully. Okay, so we need to compute the market shares given a guess for the mean utility and given the nonlinear parameters and, of course, the data. So that's what it is theoretically, right? We want to sum over all the individuals that would check. Now, of course, for some models it can be done analytically. Generally, it can't. Right? So the question is, how do we compute this integral? There's various ways of doing that. I think the most intuitive is to think of doing this via simulation. Okay? Not necessarily the most efficient. There's more efficient ways of doing that. I mean, I'll kind of talk about them somewhere down here, but let's just intuitively now see how we do that. And the basic idea is the following. What we're going to do is we're going to go and draw, NS here is the number of simulation draws. Okay, so think of, I don't know, let's assume it's 100. Okay, so you take 100 draws from the distributions of DI and VI. Right? So let's assume VIs are just normal. Okay, so you take 100 draws from the normal distribution. Okay, you go take draws of 100 people, let's say from the CPS for that particular market, and look at their demographics. Let's say income and education, whatever you need. Right? So that's your sample now. That, by the way, this draw you do once at the very, very beginning. You don't change it with every iteration because otherwise you'll have convergence problems. But you do that once. And now what you say is for each value of this delta and each value of these nonlinear parameters, you can compute what the shares are or the choice probabilities for each individual, and you're just going to sum over that. Okay, so effectively what we're doing is we're going to analytically integrate over epsilon. That's the Logit error term, right? That's implicit in the fact that I'm using a Logit-like equation here. And then I'm going to numerically integrate over the DIs and the VIs. Okay, so that's how we're going to simulate or compute this market share. Okay, so I said that epsilons are integrated analytically. As I said, there's other simulations of how to actually, draw this. So the original BLP article had some important sampling, so you don't just take a random draw. You maybe want to put, more weight on particular parts of the distribution. There's things called Holton sequences. More recently, there's actually Ken Judd and various co-authors have proposed approximating this not by simulation, but actually by quadrature, which actually ends up working quite well. It works especially well if you don't have the demographics, right? So if you're just trying to integrate over this normal draws, you can actually do it and leaving very little computational error in it by just using quadrature rules. Okay, but it's basically the same idea of saying we need a way to compute or to approximate this market share. Okay, the second step, what we want to do is we want to invert the relationship, right? So we want to basically say, well, these are the predicted market shares, right? And we want to set them equal to the observed market shares, right? And this has to be done market by market, right? So it's basically saying here's the share, the vector of market shares of all the products, and it has to equate the observed vector of market shares, right? So the question of sort of how do we do this, and as I say, some models it can be done analytically, but generally it has to be done numerically. You can just search randomly, or more kind of a more efficient way of doing it is using this contraction mapping, which say you start with a guess of delta. You use that to compute the market share from that first step, and then you use that and the actual market shares to update your guess. And you kind of do this until it converges. So basically until the distance between the initial guess, the guess h and h plus 1 is very small, right? It's below a certain tolerance level. Okay? Choosing a high tolerance level here is actually quite important. It's something I think we didn't fully appreciate early on, and we talk about some of the recent problems people have found out. A lot is related to this. So you need to compute this actually quite precisely. at least 10 to the minus 12, maybe even more. Okay? And it ends up actually, this is probably one of the most difficult parts of the algorithm, because you have to do this for every single candidate theta 2. And what happens is for some theta 2s that are really bad parameters, right, they're very far away from the truth, this might actually take a very long time. For the truth, usually it actually, this does it fairly quickly. Okay, 50, 60 iterations I found usually it converges pretty quickly for good values of theta 2. Okay, but bad values takes a very long time. Okay, once we have that, we can define our error term as this thing that was inverted, right, the result from that second step, minus these things here. Right? So now we can write the error term, if you want, as a function of the parameters. Right? So that's the error term as a function of the parameters, and the parameters are the nonlinear parameters. You can see now the name. Nonlinear parameters enter inside this function, and the linear parameters, alpha and beta, enter linearly. Okay, and now we're basically done. We form, here's the GMM objective function, right? So we take, this is the error term. We're going to interact it with instruments. Okay, so we're going to take instruments that are mean independent of this error term, and we form this GMM objective function where W is some sort of a weight matrix that we're going to use, right? And now what we're doing is we're going to search over these parameters. Okay, and because it's linear, we're going to have to do a nonlinear search. Okay, there's a couple of ways to simplify these. It ends up you can actually, quote unquote, concentrate out the linear parameters and just focus the search for theta 2. And you can use the implicit function theorem to actually compute analytic gradients of it, and that really speeds things up. But again, that's kind of in the nitty-gritty detail. The key thing is that even after all this stuff, this is still a highly nonlinear search problem, and we don't really know the properties of it. Okay, all that we know is when we've ever played around with data is it seems to be that there's quite a few local optima. Okay, and that's going to be quite important. So it's going to be quite important when you do this is to start from a lot of different search values and also try to different optimizers. Okay, and I'll kind of talk about this in a second and kind of some other follow-up work. Okay, so this is basically the BLP estimation algorithm. Let me kind of briefly talk about identification. I mean, the truth is I could probably spend a whole lecture just kind of going through the formal details of identification, but it gets pretty messy pretty quickly. So I'll actually refer you kind of at the end for kind of proof and a lot of very useful discussion through recent series of papers by Phil Hale and Steve Berry, where they actually talk about identification, non-parametric identification of these models with aggregate data and with individual level data. But let me here try to talk through things a little bit kind of informally. So ideally, how would we want to identify these parameters? What's the ideal experiment? So the ideal experiment that we want is we'd want to randomly vary the prices and the characteristics, and maybe even the availability of product, right? So think of it as saying an infinite price. And we want to see then how do consumers switch, right? So when I take away, your favorite car, which cars do you go to, right? That's how I'm going to get, the substitution patterns, right? Seeing what's your second choice. And maybe I don't see this for each individual, but I want to see in the market, right? And that's what's going to tell us substitution, right? So if we take away the Mercedes and we see that nothing changes except the share of BMW, that's going to tell us something about the substitution pattern. On the other hand, if we take away Mercedes and the only car that increases its sales is a Honda Civic, that's going to tell us something else about substitution patterns. Okay, unlikely, but could be. So what we're going to try to do is, in practice, so that's the ideal experiment. Now, note that it's actually, to run this ideal experiment, it's actually almost impossible, right? Because we're going to have to change, one by one, all the products and all the characteristics of all the J products and see where all the others go, right? So it's not just let's take Mercedes and see what else, happens. It's like, let's take one by one the 100 cars we have and see exactly where the shares go. So it's a lot of these series of experiments, but that's kind of what we're trying to do. So in practice, what we're going to try to do is we're going to try to get, instruments that kind of mimic the same idea. Is to say we're going to try to have instruments that are going to impact, in ways that we believe are exogenous, the choice set, or at least the characteristics of the choice set. And after lunch, we'll see examples of this. The key issue is do we have enough variation to identify substitution? And it ends up that even though in theory, these models could even be identified maybe with a single cross-section, especially with parametric assumptions, Okay? In practice, we need to have more variation. So in practice, to actually get any estimates, especially of the nonlinear parameters, we really need to add one of three things, or at least that's what the literature has done. I mean, maybe there's others. One is to add supply information, and that's what the part of what the original BLP paper did, and Ariel will talk about that later. The other is to add many markets. So they have not just a single cross-section, but they actually have a lot of variation across markets and in the demographics. That's what I did in my work on cereal. And then a third piece that's actually been very popular and very useful is to add some form of what's called micro moments, so some sort of micro information, and that's what Emil Petrin did in his minivan paper that came out in the JPE, or that's what BLP did in their so-called micro BLP, all of which we'll talk later on. Okay? So all these are actually very useful ways in kind of helping with the identification. Okay, so that's just kind of a very quick and informal and probably kind of not doing justice to exactly kind of what's going on, but we'll kind of see more as we move along. I talked about estimation. Let me just say just a quick word about the about inference and the limit distribution. So in principle, we can get the standard errors the way we always do out of a GMM estimator. So with a single cross section, it's basically some form of the of this equation, right? So we basically have the derivative of the expectation of the moment with respect to parameters and the variance covariance of the moments evaluated. There's this variance covariance matrix really has 2 or 3 components to it, and that's what makes this a little bit different. So one is just randomness generated by random draws of the error term, right? And that's kind of the usual variance that we have in any sort of GMM. What's here is we also have potential variance generated by simulation draws because we have to compute the market shares by simulation. And then there's a third part that we usually assume away, and that is that there could be some noise in our estimates of the data of the market shares, right? Because they're based on some sample of consumers. So a lot of times we'll assume it away because we're assuming it's coming from administrative data where you literally have the population, right? You know exactly how many cars GM sold, right, in any given year, and there's kind of enough consumers to do that. But if it's actually based on samples, especially small samples, especially if the market shares are small, there could be noise in here as well. So it'd be kind of the three sources. So basically, as Barry, Linton, and Pecos show in a restud paper, these last 2 components could actually be very large in large market shares. If market shares are small, but otherwise we basically can use the following, the equation up there. A separate issue that I'm not going to get into at all is in what sense we want to do the asymptotics, and what state do we want to look at the limit. Do we want to look at it in J the way we have it there? So that's saying basically we're looking at a single cross section and the number of products is going to infinity, or maybe what we want to look at is the number of markets. And there's a lot of subtle issues there that I'm not going to get into, and it really depends on the structure of the data, right? So in many data sets we have a lot of markets and not that many products. So you might think that what we want to do is the asymptotics are in the number of markets, and then things change a little bit. But for the most part, the basic idea is we're going to use the basic formulas and change them. Okay, so that's it. Let me now go into some kind of recent work that has talked both about some challenges with this algorithm, and then some alternative computational methods. I'll just survey them quickly, and then I'll finish by actually showing you some relative performance of these different algorithms. Okay, so a recent paper by Chris Knittel, an ex-student of his, found that different optimizers gave very different results and were very sensitive to the starting value. So what they did was they took, I think it was something like 10 different optimizers. Don't quote me, I might get the exact number wrong, but it's that order of magnitude. And I think started each of them with 50 different starting points. Okay? And then what they gave is they said, here's the distribution of the numbers that the algorithm spit out at the end. And it was a very wide distribution. Okay, you got a whole range of different numbers that the different optimizers got. Now, they're a little bit silent as to exactly what we should take away from this exercise. Some people have actually basically said, well, this basically tells us this whole algorithm or this whole kind of line of research doesn't work. I definitely have a different take on it, but that's what some people have taken. So let me just sort of point out a few things. Is the fact that what what they did is not exact, doesn't really mimic what any, I think, reasonable researcher will do in the following two sense. First is, it's unlikely you'll take just one starting value and say, oh, I found an optimum, that's it, I'm done. Okay? You're probably going to start from at least, several more. I mean, ideally a lot more, but you'll start from several more, and then you'll kind of realize, wait a second, I'm actually getting different ones. Which is the one that actually has kind of a lower value of the objective function? That's the one that I want to look at. Right? That's one thing. The other thing is that they actually took a few of these search algorithms that are actually known to have very bad properties, and it's not like the ones that people use in practice. Okay? So it ends up that one value and say, oh, let's just find what it is. Right? So there is a very clear kind of caution here, which is, these are still highly nonlinear problems. And everyone sort of say, oh, we hope that one day Stata will actually be able to do this for us. I think that when that happens, I mean, it's going to be a big problem, because I doubt, that, I mean, unless Stata will actually built in and force you to do, specify 100 different starting values. Otherwise, we're not going to give you parameter estimates. But otherwise, one should be very kind of cautious in doing that. Right? So there's a very clear warning here about the challenges of nonlinear estimation. I think that's at the end what these guys are trying to say. However, it has kind of led a bunch of people to say, well, maybe we should explore alternative computational algorithms. And indeed, Judd and Su, and then in a separate paper, Dubé, Fox, and Su, advocate the use of a different, slightly different algorithm. It's called MPEX, stands for Mathematical Programming with Equilibrium Constraints. And the basic idea is actually quite simple. What they're going to do is you're going to maximize the same GMM objective function as we did here, except that it's going to be a constrained optimization problem. Okay, and the constraints are going to be the equilibrium constraints. So what they want is at the optimum, they want these inversion conditions to hold. Okay, I'll put up equations in a second. Maybe this will be clearer. And what this does is it says it basically avoids the need to perform the inversion in each and every candidate value of the parameter. Right? That's why it's very costly here to do, because some of them are, you start by looking and say, okay, this is a really crappy parameter guess. Okay? And it's going to take forever to find the delta that actually equates, because it's a weird parameter. Right? But the inversion has to do that. Right? It's going to spend thousands of iterations trying to actually get the contraction mapping to converge, and this avoids that. And it ends up that, even though you'll see in a second, they actually increase the number of parameters by a lot, and I'll make it clear in a second, it can actually solve, now with kind of modern optimizers, for example, quite common is this thing called Nitro. So if you use Nitro, you can actually solve problems that are quite large. You can actually solve it quite efficiently, and indeed, they actually report significant speed improvements and better, much more stable properties using this alternative. Okay, so let me tell you kind of what because really all I need is basically this one equation. So formally what they're going to do is, remember, before what we had was the same objective function, except the x's were a function of theta. And we minimized just over theta. Okay? So now what we're going to do is we're going to make these x's, they're going to be parameters themselves. Okay, so what we're searching is over theta and x's. And remember, these x's are actually very high dimensional, right? Because there's one xi for each observation, basically, each product in each market. Okay, so we're going to search over this high dimensional space, but it's the same objective function, right? Except that now it's a function of, the x's directly, subject to this equilibrium constraint, right? So this inversion that we had, we're now going to say the predicted market shares have to equal the observed market shares, right? So at the optimum, right, this is going to satisfy exactly the same conditions as the GMM objective, as the BLP objective function. Right? So in terms of statistical properties, it's going to have exactly the same statistical properties. This is just a way of finding that single point. Okay, and as I said, the key thing is that you actually avoid the need to do the inversion for each and every candidate value. In some sense, you're only requiring that it holds at the equilibrium. Okay, and of course, if we actually, there's subject to actually finding the optimum correctly, this should actually yield the exact same solution as the nested fixed point. Now, of course, there's actually many bells and whistles on how to make this faster. I skipped all of them, but that's kind of the basic idea. Let me talk about another alternative that's recently been proposed. Okay, and I actually put this up with some hesitation because this is actually a working paper that hasn't actually gone through all the checks and stuff. So there's actually a non-zero probability that this is all wrong, and we haven't found out. But it actually seems to work reasonably well. So with that, disclaimer, I hope we have it on video. So I actually, when I get angry emails from various people, hopefully that disclaimer will guard me against it. So the basic idea here is actually it's potentially a very simple idea, and it kind of builds on ideas that we've seen in dynamic choice problems. And it's the following, saying what we want is we want this share equation, right? So, so this is basically, if you want this, switch notation here a little bit, this is basically the inversion, the thing that we're inverting, right? So we say, let's approximate it by first order Taylor approximation, right? So it's basically, this thing evaluated at some candidate psi 0, so let's take a guess for it, plus this derivative. Now let's set this approximation equal to the actual shares. Okay, kind of what we're trying to do in the inversion, right? Well, this now gives us, if you want an approximation, right, just kind of rearranging things, an approximation for psi jt, right? Just kind of using this first order approximation, right? Just this term here. Okay, and the basic idea is saying, well, suppose we did this, we can now put this in to the, right, to the GMM objective function, right? So give me a guess of psi, of psi naught, this guess. I can use that to approximate psi t, and then that's what I'm going to plug in here. Okay, so how am I going to turn this into an estimation algorithm? It's basically the following. It's kind of, these kind of two steps that are iterated until convergence. So I start from a guess of this psi naught. I use this guess to compute a parameter. Right? I put it in that, kind of pseudo GMM objective function. I get this guess, and now I use this guess to update my guess of psi. And then I iterate back and forth until they converge. And converge here both the parameters and the psi's. Okay, so very much like what we're doing in these other algorithms, right? We want all these conditions to converge, right? But in some sense what we're doing here is we're changing the order of the nested fixed point, right? The nested fixed point, we're searching over a parameter in the outer loop, and in the inner loop, we were searching for the psi's. Right here what we're saying is to say, let's switch the order, right? So let's start with a guess of the psi and then converge the theta and then update the psi and do that. Right? So very much like NPEC, it avoids the inversion at each and every step, right? But has a low-dimensional search. Unlike NPEC, right? Because here the search, remember, when we're searching here for the GMM objective function, it's nonlinear, it's only over theta, which is a fairly low-dimensional space, as opposed to having all these psi's. So potentially has the benefits of both. Okay. Once again, this disclaimer. There's some proofs in the paper that show things. Those proofs have still yet to be vetted through kind of the usual process. Okay. So let me just finish by actually showing you some results of actually a student of ours that graduated a few months ago. He's making a lot of money now at a hedge fund. But before he went, he needed a quick thesis, a third chapter for his thesis, and we were trying to think of what would be a good thing to do. He is a very good programmer, probably one of the best programmers or RAs that I've had. So I thought, you know what? I've always been curious about the different, how these works. I know all the authors always present results, but we all know what it's like, right? If you propose a new method, somehow it always works better than what was before, right? I mean, the incentives aren't aligned, right? You want someone that's not tied to any one of these to try to do that. So what I had him do was run a bunch of Monte Carlos, and I don't have the details of exactly what he ran, but a bunch of Monte Carlos that tried these three different alternatives. Okay, so the three that he tried were MPEG, what he called nested fixed point, which is the original BLP inversion, and this ABLP. Okay, there's a lot of details of exactly how he did this, which I'm going to skip, but maybe I could detail a little bit as we go along. And what he has here, what I have here reported is for, he had a different number of markets varying from 50 to 2,500 and different number of alternatives or products going from 10 to 50. And for each one of these, this is the conditional on convergence. So conditional, they actually got a number. What's the average time in seconds until convergence? Okay, in all of these cases, it actually converges. It's a Monte Carlo, so he knows what the two parameters are. So this is convergence to the truth. Okay, he actually, I think, did not have in his Monte Carlos a lot of problems of getting to local optimum. At least I believe that's the case. So before I actually go kind of compare this, I think the one thing I want to point out, even though some of these problems are actually fairly large, right? So 2,500 markets with 50 products, that's a lot. You rarely will have so much data, right? The original BLP paper that we'll talk about at lunch had, they had 20 markets with about 100 products, so about 2,000 observations overall. So it's not quite, it's somewhere kind of in this range. It's not exactly on here, okay? So the key thing to note, these are seconds to convergence. I think the first thing to note from this, it doesn't take that long, okay? So maybe this whole idea is it this, is it that, or whatever, maybe that's not the first order thing that we should worry about, right? I mean, because even the highest number here, right? I mean, this is, about 1,000 seconds, right? It's about 15 minutes, okay? I mean, that's, I don't know, I'm starting to feel my age when I say, oh, I remember when we first started doing this, you wait a week to get, a single convergence. So, and it's pretty simple. Now, in terms of performance, generally what you see here, and this is actually starting from what he called theta c, so it's a relatively good starting value, right? So he knows the answer, so you start relatively close. And generally what you see is there's some variation in this. He didn't get, MPEC or the nested fixed point. I mean, sometimes one is faster, sometimes one is not. The nested fixed points tend to do much better when you get to larger problem, because here now the dimensions really start kicking in, the fact that it's a high dimensional problem. But the thing that actually seems to do quite well is the ABLP. And similarly, when you actually go now, the same sort of idea, but looking from a further point, here he actually had a problem of even getting any convergence with MPEC, and it's actually known that some starting values you can't even, MPEC doesn't start, so you have to restart it from a different starting value, just because it really can't find anything that's to satisfy the constraint, just the way that it does the search. So overall, he was actually getting, I would say at best, kind of mixed results with MPAC and very good results with the approximate BLP. Just a word of caution here. I mean, I'm sure that the MPEC results here could probably be significantly improved. So if you actually took his code and gave it to Fox or Sue, I'm sure they could actually do it significantly faster. The way that I see it, this is not actually testing which algorithm is faster, but in some sense testing kind of an RA, a good RA, and saying, okay, I have an RA, I gave him kind of doing this, what could I expect? And what I've learned from this, and I've actually heard it from others, is that the MPEC, once you get it going, you get all the bells and whistles, is probably going to be faster, but it actually takes a bit of an effort to do that. So just a word of caution in terms of the computational time. But that being said, I mean, as I said, these problems with real data are actually highly nonlinear, and the problem is not to get, a long time to get a single parameter, but you really want to, beat at it as much as you can, start with as wacky starting values as you can, and throw different optimizers and different algorithms in it. So the idea is, even if one of these is slower or faster, I mean, I would recommend trying as many of these as you can to guarantee that you get a reasonable answer. Yes?
Are you coding this in MATLAB, number one? Number two, is there any CAN code out there?
Yes, good question, thank you. So in terms of CAN code, so for a while, the nested fixed point was the code that I put online. It's still available at sort of places. There's a couple of ways in which it can improve, or a couple of ways which it's wrong, and I haven't actually bothered sort of updating that. The MPEC code, Sue has on his webpage actually very detailed code. I believe that either Sue or Fox might also have a kind of updated code for the nested fixed point. So there are codes that are out there. Both of these, I believe, are in MATLAB. The MPEC, basically what it does, what you'd want is you want to have this nitro optimizer, right? Because if you don't actually have a good constrained optimization program, it's going to take a long time because its dimensions are higher. So you need a very efficient one. People seem to be happy with nitro. I know Ken Judd recently has used a different optimizer. The name, I forget the name, but nitro actually comes, there is now a direct interface with MATLAB, but it's a separate one. My student, by the way, I didn't report that here. This is with MATLAB. He did find that actually programming these in C, you do get significant improvements, especially for that market share equation, because that's called over and over and over thousands of times throughout the algorithm. So writing that in C really helps. Again, for me, I'd rather have it take another 20 minutes rather than spending, 2 weeks or more trying to program it, but that's fashion. The other thing in which you can speed this up is by parallel processing. So MATLAB today, if you actually have the right toolbox, what you can do is write a loop for this for each one of the markets separately, and that's it's just a different command. It's a P4 instead of a 4, and basically then it takes automatically whatever you have on your, well, whatever, how many processors you allocate to it. Okay? Anyway, I'm happy to talk more about it. I suspect that's a little bit too nitty and too gritty for at least several of the folks here. Any other questions?